yes, it's when you have many, just to be in coherence with some recent advances in quantum integrable systems at the end. And it works because, indeed, I will discuss two different ways to consider algebraic Bethe ansatz. And in fact, I will not discuss the old way, and just show a few new things that happen when you break what is called U1 symmetry. So this is, I will not make some big story, but basically the problem is the following. So in the previous talk, you have, in some sense, the end of the story, or what's reached the end of what we try to do. But at the beginning, there's this question to have Bethe ansatz. And this Bethe ansatz, it's a way to transform basically the problem of diagonalization of huge matrix and find eigenstates and eigenvalue, and in particular just parameterize this object in terms of auxiliary parameters. So I will what we call Bethe roots, a set of parameters. So I will not give all the equation, but the main idea of Bethe ansatz is that, okay, we have to diagonalize some Hamiltonian or maybe something else, and we should characterize all the state of the system just in terms of an auxiliary problem, so solve some system of algebraic equations, the Bethe equation, and this object will be function of this parameter. And the algebraic Bethe ansatz, this is the same, and eigenvalue will depend on you. So come from the beautiful work of Fadeyev's school and the discovery of what is called the quantum groups, and in particular, so quantum groups, it's just, well, there's a lot of story, but you have this R matrix, but you have an algebra, associative algebra that is given, can be given in terms of what is called RTT formula, or if you consider model with boundary, it's reflection equation. But it's this object, this algebra, you can extract transfer matrix that was discussed in the previous talk, and there are the algebraic framework between many of the integrable systems. Up to now, maybe there's other structure, more complex structure, but basically you have this quantum group. And algebraic is the way that the use of this structure to characterize, to recover the solution of Bethe. And one of the key points is transfer matrix. So this object is some matrix that contain elements depending on the type of algebra behind. For SL2, it's just 2 by 2 matrix. And Hamiltonian is given, can be extracted from the transfer matrix that is the trace of this object, T of U. And for the model that's considered Bethe, that is XXX spin chain periodic, you have a conserved quantity. In particular, you have the total spin that it conserves, so it commutes with the Hamiltonian, or it means that it commutes with the transfer matrix. And in this case, you have different sectors, and you can split this problem into different subspace depending on the number of parameters you use. And each one corresponds to quantum number of total spin. But if you have models sometimes that do not have this property, usual algebraic Bethe ansatz, that I will not describe totally here, fails. And what is the recent advance, for recent advance last 7 years, more or less, is to understand it's mostly for finite dimensional model, because for infinite there's problems that all I will say don't work for the moment. It's, could we use this algebraic Bethe ansatz? And the answer, so at the beginning of my thesis, that my thesis was here about algebraic Bethe ansatz for higher spin, higher rank model. And could we compute things for this model without U1 symmetry? So you will have different tools that's alternative to Bethe ansatz, algebraic Bethe ansatz, to consider such model, like separation of variable. But what we discovered is that we can also do everything in terms of this algebraic Bethe ansatz, just modifying few things. So what's the advance during this time of research? So this research is the joint work with many researchers. So at the beginning with Eric Ragoussis, that was my PhD director, and after Crampé, Slavnov, Pimenta, Vallée, and more recently we start to make numerics. So this is just because I'm very happy because I have at least 3 or 4 pictures in my whole work, and there are some plot of Bethe roots. Maybe if I have time, I will discuss what we are looking in such picture. But what's the thing we basically do? It just shows that many objects that was known for model with this U1 symmetry are actually also known. We discover the version without U1 symmetry for finite model. And basically the first key point is to find what is called the off-shell action of the modified transfer matrix, or it's basically the transfer matrix acting on Bethe states. And there are some specific structure, and the knowledge of this structure has appeared. And just last year, we show that this off-shell action allow to prove formula for scalar product just using linear algebra and have very simple and stupid proof, but not stupid, but yeah, regarding to all the previous technique and all the way, it's so simple. And it's just linear algebra. And come from a discussion with Nikita told me that when he presents this to mathematicians, they always say, oh, but all this is just linear algebra. It's not. And at the end, yes, it appears that this idea and this remark, we arrive to obtain this linear set. But it's also citation of Jimbo, okay, but I'm not. It's only linear algebra. So yes, just come back to the master and say what we have. So basically, so you have this off-shell action. So it's the basic point. When you have this, in fact, you characterize the Bethe states, you characterize the eigenvalue, and you also characterize the Bethe equation. And so it appears the structure of the off-shell action is the same independently of the presence or absence of a U1 symmetry.
Sorry, could you maybe just say slightly more precisely, when you say you don't have U1 symmetry, do you mean that your twist matrix is not diagonal? Is that the same or you mean something different?
It just means that yeah, because this story of for x66 for twist matrix, if you don't have singular twist matrix, you can always make diagonalization and you can make a global rotation. But it's not true if you have a boundary case. Oh. And basically all the work, because all I will present is for x66, it's just because it's more simple and you can see all the features of these new techniques. After all this should be translated to boundary case, and then we can expect, and in particular, this the off-shell action for boundary case is known, so it means that this way to doing gives directly scalar product.
Can I also ask something? Is it also, you also have in mind the 8 vertex model, for instance?
It was done by Nikita and other guys that year for XYZ. It seems, I don't read the paper in detail, but they use XYZ and they...
For the XYZ model or for the corresponding S model? That was my question. If you can direct...
Oh, yes, we should look to the paper, because I do not participate to this part, but I think it's a XYZ spin chain. But we just look on archive and we have the answer. But yeah, and but maybe after you have subtleties, and in particular for this part, there are maybe things to learn if we consider higher ranked model. Because here there's no more linear algebra, the system is very more complicated and it's still open problem. But I will come back on that. And second point is, so this is just something when you have this modified transfer action, you can show that you have different way to write down the Bethe vector. You have different type of eigenvalues, so you can write a Wronskian equation. So, and the Wronskian equation appeared recently to be discussed a lot because it's allowed to make numerical calculation by Volin and collaborator, and to also appear to be useful to characterize better roots, at least numerically, and maybe in separation of variable we will learn also more on that. But the point is it was quite easy to see that we have also a modified version of the Wronskian, so consequence of this equation still to be understood, but we wrote it, and recently was done also for open model by Nepomechi. And for all these things, we produce a scalar product. So scalar product is first step to go to correction function. And that's, we made a conjecture a few years ago with Pimenta, and we tried to prove it in different ways. So to do this, we found with Nikita a very complex proof, and we were not happy about that. And finally, we found this very simple way to prove this scalar product, and in particular in the on-shell, off-shell case. So I will come back on this definition after, and also we have the off-shell, and in this story we found in this context what we call modified Isargin determinant, and it's basically a partition function on rectangular lattice. That was also so before. So basically what changed for this, so sorry for the people that don't know nothing about Bethe on that, but basically this, the question to find the transfer matrix, so I will reverse the process, this is the transfer matrix, so that's contain a conserved quantity of the model we consider. Here it's in the formally for XXX twisted spin chain, so it's there is the simplest case, and we have just here some additional matrix with just C number that is non-diagonal. And in this case, we show that modified action have the similar form for standard case, with the lambda is this eigenvalue. So usually in standard case, we don't have this term, and Q, it's Baxter polynomial, and Q in this case, Q plus minus, just because we have two family for the Wronskian, but it's just a simple polynomial of that form. And here the number, let's say S, depend of the type of representation. For finite dimensional representation you choose. So for spin 1/2 is just the number of sites. But for, if you consider a spin chain with arbitrary spin, S is just the sum of all the spin, maybe with the 2 in front. Yes. Yes, with the 2 in front. And this first difference between the usual case, that's this S depends on the type of representation. And this equation can be found only if you fix the representation. In usual algebraic Bethe on that, you have a freedom, you just have to say that you have Eigen-West representation, that it contains a lot of also infinite dimensional model, like a Bose-Gaze, etc. And difference, it's the Bethe vector, so U bar, this it just means the product of this object that is an operator. That is a linear combination of these T that are the entries of this object, the monodromy matrix, and there are formal series, but in algebraic point of view, they are just formal series of operator of the modes that are the algebra. And if you represent, they are just matrices. And usually, you just have only this term. And you have some transformation of the transfer matrix that's allowed to find. So this, we understand how to obtain this type of vector. And basically, this reproduces a result that arrives from another point of view. That's what is called off-diagonal Bethe ansatz. So that shows that in many type of models that you can consider a model with a T1 symmetry, just adding a new term and fixing the number of 0 of the Q. So this was some very new state, and how
much unique is this gap? It's something that is almost always possible.
If you fix Q to be minimal, you have at least for SL2 case, you have one case for the one I studied. After, for SL3, it's still open problem to understand. You can understand if you have some nested, that you have some first steps of the nesting that have a U1 symmetry, and the next one don't have. But for some SL3 model without any U1 symmetry, this is, for me, a big problem. If someone finds this, I'm very happy. If it exists or not. But this is the main obstacle to extend this to SL3 case for the moment.
Operator interpretation like a Q operator. And F, does it have an operator interpretation like Q operator? You can deal with operator?
Yeah. This, I agree, but yeah, here I put Q because I think it's used to the next slide about the modified Wronskian, but basically it's some functions that at the beginning you could not relate to Q. And because the Q you use in SOV are, in SL2 they are the same, but for SL3 for the moment I don't understand exactly if they are a match. And in particular, the point is for SL3 I would like to see a Q and P to be the two family and not just one. And this is why, because I would like to have a very simple limit to the diagonal case. And so it's why it's a bit different. And understand the link here. But for SL2, we know that it's the same objects. But for SL3, it's not clear. So basically, this is this new term, and we obtain all this formula. So it was done firstly for open case, and where we conjecture the Bethe vector, and we can understand the origin of the F in algebraic point of view. After I developed for XXZ with myself, and after with Pimenta and also Jean Avant and Grosjean. And so it was the first stage, and we also prove that indeed, because at the beginning it was a conjecture, and after we understand different way to prove, in particular also just using orthogonal basis, like a separation of variable basis, and you have very deep connection between this object and also the separation of variable basis. Some of the different cases, but I will not discuss here. And basically, if you do this, you can do this also with another type of operator. So here it's creation operator, modified creation. You can also do the same thing with modified annihilation, and doing the both sides, you can produce this modified Wronskian equation. And the difference, it's for usual case, this is 0. And so it means that this is some kind of Q difference, that should be some constant. But in here, and also, here we have this new term that appears, but we have also this Wronskian equation. So for the moment, I'm not sure that it will help in connection with this fast analytical solver or what it will do, but just it was during the calculation and the research of scalar product, we realized that this can appear. And so maybe it will be helpful in some point. Who knows, like say Nikita. Okay. The other thing is to have this scalar product. So basically for usual algebraic Bethe ansatz, it was proved by Slavnov in the 80s, at the end of the 80s, that when you have a scalar product of two states, and so you have two family of parameter, and one satisfies the Bethe equation. So Bethe equation, it was this part. So this equation, when you put this equal to 0, it makes this term to be null, and then you have its an eigenstate. And in that equation, we say off shell, the set of parameter, it's arbitrary, even formal parameter. And if we fix this Bethe equation, it became eigenstates. So in that case, it was known that for usual Bethe ansatz, you have this formula, and it's given in terms of determinant, and Young's group shows that this determinant is some Jacobian of the eigenvalue. So we start with this form and with Rodrigo Pimenta, and we say, okay, basically we would like to have nice diagonal limit, and so we should expect to have some similar structure, and with different argument, we we find that you have a new prefactor. So you have this difference, it's this new eigenvalues that contain the new term. And you have this new prefactor that is some kind of partition function. And later, doing this calculation, so we spent a few times before we try different way to understand how to prove this. And finally, we start to just ask the usual way to start to calculate off-shell. So it produces what is called Isdergin-Korepin formula. So it's a huge combinatorics formula with some of the partition of subset of this, of the union of these two set of parameters. And it contains Isdergin determinants, that is determinant that represent partition function, domain wall partition function. So basically you have square with domain wall boundary condition, and this, so it's what called some case that it's determinant, Isdergin determinant. And doing this, so we use also many knowledge of calculation we did for SL3, in particular what is called multiple action. So what was the work that I don't discuss here, but calculation about SL3 scalar product, done a few years before this work with all this guy. In particular, that was first formula for form factor for SL3. And in particular, at this point, we generate what is this off-shell action of the transfer matrix and identify all the off-shell terms. And that appear to be important. For example, that's a formula by Wheeler about some integral formulation of scalar product, but for the moment it's still not very useful, but it appears to be interesting to have this information at many points, and after there's a lot of development on this. But basically we calculate the multiple action and we find that you have a new Isdergin determinant, but it's, in this case it corresponds to a rectangular lattice model. And at the end, so we succeed with a very, very difficult proof that mostly done by Nikita. We found to prove the modified Slavnov and Godard formula. So Godard formula is when you put both sets on shell, and it corresponds to the norm of the vector. And so basically, this was done. All the work was done for x66, and we conjecture also for x66 twisted. We conjecture for open case, and now more recently, and it's my last point, and in some sense the most interesting. Yeah, we realize that we can rewrite the scalar product for Slavnov formula just in terms of a linear system. So here this formula for spin 1/2. So you have n+1 variable, and you use, basically the idea is very simple. You have the transfer matrix, and you compute from two different ways. So you want to compute this scalar product, and this one is on shell and this one is off shell. You just put here the transfer matrix. You act on the right, on the left. It gives two solutions. Here it just gives a function that corresponds to this part. And the other side gives transfer matrix eigenvalue for the U and the unwanted term. So here the set, usually it's given by 1 up to n. So here we add 0. And we can reproduce all this equation just by permutation of this set. And so we give all the sets of equation. And we have n+1 times n+1 matrices, and the x are just the scalar product we are looking for. And you have to check that the rank of this matrix is given by n. There are some subtleties that I avoid here. And if it's the case, basically, you know by Cramer's rule that the determinant of the minor of this object is the solution. And indeed, it reproduces the solution. I have no idea of the time. 2 minutes, so it's perfect. Okay, and basically, actually, so yes, I just found a position 2 years ago, so I slowed down a bit the research, but basically the scalar product for open XXZ case is just question of time. But method is direct, just finish an asymptotic to fix the coefficient, but it will have the same form. We also look last year, because Nikita spent a few time in tour, and we tried to mix compute scalar product of usual Bethe Ansatz and modified one to maybe imagine some quench things that you, but or just to see if we can find some determinant form, and the answer is yes. In particular, it's just mostly the same thing, but you have just one row to modify. And maybe I don't know if there's a link about your remark about this plus-minus case, but there's few modification. And but maybe after it should be more interesting if we can after reproduce for open case. And this was also other discussion with Bazillac and question of hypergeometric function, hypergeometric function, and but this I'm not the expert, so let's forget. But there's maybe some motivation to use this for open case. And so the main problem, and it's why I put the plot, it's if you, for people that remember the beginning of Bethe Ansatz, so before the understanding of the distribution of the old and the ground states, they make numerics to look the structure of the solution of Bethe equation and see all the Bethe roots where they are in the quantum space, the complex plane, sorry, and basically this picture is just depending of the number of sites. For this case it's x66, but where you consider the version with, it's very the model considered by Bethe, but we consider this model starting from the equation with an homogeneous term. And the ground state, you have n over 2 Bethe roots, so the set is fixed, but here we have in any case n roots, so there's more roots, so there are this line and that line and all these roots here that are new in terms of yeah, this is the Bethe root for the ground states of x66, and this small part are the real line and the usual yes, but for the x66 periodic considered by Bethe. And so basically the particle old part is just here. And so what we would like to understand is, okay, what other type of roots will appear, and the idea after to see, can we go to thermodynamical limit? And in particular, what's up here, what should be the contribution of this object? So in that case, we saw that this part just changed the factor in terms of the two terms of the eigenvalue, and all the other part goes to infinity and kills the inhomogeneous term. So basically you come back to the usual case in the thermodynamical limit, but at least it's what the numerics show. And here we start to look for x6 with a boundary case. So it's x, this case is just xx with a upper and lower boundary. And after we would like to try to deform to x6z and see also if we have the same structure or if the inhomogeneous term disappears also, and if it's the case, so basically we can end the question and come back with the usual technique for that. But so for the moment we don't have the answer, but this is thing we would like to understand. So this done by with Rodrigo, This x66 was done with variable, and there's Julien Garot, and also I have discussion with Alexis Morin-Duchesne about this x6 case, because you have techniques to do this using some quadratic equation. Different way, and maybe we should compare different way. And finally, this twisted x66 for SL3 still, it's done for lower block twist matrix. It means that the first tape is usual and the second tape don't have U1 symmetry. But I would like to have the full case, and this means that I should understand this new TQ equation for SL3. That in the actual literature, there's proposition from this Chinese group, but this destroys the usual structure, or in the SOV version also you have new type of Q operator, so it seems for me a different question. Or maybe this what I'm looking for don't exist, but so this for the moment we don't know. So open problems that should be to generalize this Kramer's method to SLN.
Very short question. Just a remark. Okay, you have this PQ equation with the modified term in general, just for the asymptotic to get that the two sides of the equation have the same asymptotic. You have to compensate it. You are obliged to do it if you want a polynomial. But for example, for the xxz case, you can also add a characterization by an ordinary TQ equation.
Yes, open case also.
You change when you change the periodicity.
Yeah.
So, basically, you can study also using ordinary TQ equation.
Yeah, I know. Yes, but it's not what I'm looking for. But yes, I know that, and in particular, the question is what are the structure of the states in this case, or we can write the states. And also, at the end, I would like just to see some scalar product or just formulation of everything in terms of beta roots. It's my question on this, and for sure you can do a different way. And at some point, it should be interesting to ask, okay, what's the advantage? Or because also in separation of variable, at some point you come back to this beta roots.
But what I was saying that for some model, at least you can prove that there are two equivalent formulations.
Yeah, from this point of view. But the point is, okay, what are the two formulations of the states? Because I just follow the states, not the eigenvalue, in my way of thinking the problem. Okay.